Okay, today we're talking about finding limits algebraically, 13.2, which is to say enough of graphs and tables of decimal approximation. Let's find limits the expedient way. To start, we need laws. Lots of laws. Limit laws. Suppose that c is a constant and that both the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. Then the following hold. If you add f of x and g of x and take the limit, it's the same as taking the limits of f of x and adding it to the limit of g of x. Subtraction also works. Multiplying by a constant inside the limit is the same as multiplying the limit by the constant. And multiplication also works as you would hope it does. Division. We say that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x over the limit as x approaches a of g of x. Now, there is an important qualification that we must add to the last rule. What is it? And no, I'm not going to tell you right now. You'll need to think about this and loop back at the end. If you already know it, go ahead and write it in. But wait, there's more. No, really. We can say that for exponents, the limit of a function raised to a power, and remember, functions could be very similar. This could just look like limit as x approaches a of x to the n. That would be the same thing. That's the same as doing the limit as x approaches a of x to the n. That's all that this means. In a related fashion, the nth root has the same property where n is a positive integer. Again, 7 triggers a caveat. We have to be careful with the rule above. What could be a potential problem? Think about what roots do. It is essential that for even values of n, limit as x approaches a of f of x be greater than 0. All that's saying is that, say that this was a square root or a fourth root, we will not deal with complex imaginary values. We wouldn't take the square root of a limit that was negative. This rule does not hold if that was to be the case. Okay, I hope that you're seeing the sheer number of laws here as a tip-off. It should be. It should be a tip-off that we are skimming the surface of a much deeper subject. While the laws themselves may be easy to accept, an entire branch of mathematics called real analysis arises in the process of proving them. And clearly that's not what we're doing for the rest of this packet. You should simply take on faith, or take on the limit laws as tools with a soupçon of awe for their origins. Okay, moving on. So the bulk of our time is not going to be hashing through these laws. The bulk of our time is going to be using them. And here's the way that we're going to structure that. First, A, we're going to use the limit laws to calculate limits if we are given numerical values for functions, f of x and g of x. And secondly, B, we're going to be learning common algebraic tricks that make simplifying obstreperous functions easier so that we can do the thing in part A. So, number 1, suppose that the limit as x approaches 2 of f of x equals 1, the limit as x approaches, pardon me, it's all approaching negative 2. The limit as x approaches negative 2 of f of x is 1. the limit as x approaches negative 2 of g of x is negative 1. We want to evaluate the limit as x approaches negative 2 of f of x plus 5 g of x. Well, if we refer back to our laws, we can see that we're allowed to break this up. This is the limit as x approaches negative 2 of f of x plus the limit as x approaches negative 2 of 5 times g of x. Furthermore, we can say the limit as x approaches negative 2 of f of x plus, not equals, silly Nathan, plus 5 times the limit as x approaches negative 2 of g of x. So let's think about what laws we just leveraged. Let's scroll back. Okay, so we used law number 1 to break up the addition. Then we used law number 3 to pull that constant, the 5, out in front of g of x. Let's go back down. So we'll say law 1 and law 3. Now, I'm not going to require you write these laws out each time. I just am doing this the first round so that you are clear on how they're working and what we're doing. Oh, Notability, don't freeze on me. Okay, restart. There we go. So we'll call that law 3. Now, back to it. Suppose that the limit as x approaches 1 of f of x equals 2. I want us to evaluate the limit as x approaches 1 of f of x quantity cubed. Now, this is referring to law 6, which says it's fair to take that exponent and pull it out. So let's go back down and see what the rewrite would be based on that law. We'll just note we're using law 6. Law 6. So what we're saying with law 6 is that the limit as x approaches 1 of f of x cubed is going to be equal to the limit as x approaches 1 of f of x with the whole thing cubed. And that is easy because we know that that's 2. Limit as x approaches 1 of f of x is 2. So our final answer here is 8. Speaking of final answers, I must have been distracted by unhappy children in the background of my house because I never did the final answer for number 1. Let's run that. So that looks like 1 for the f of x plus 5 times negative 1 for the g of x. So that should give me 1 plus negative 5 is negative 4. Okay, moving on. So last problem in this type of problem, we've got values for limit of f and limit of g, and then we're asked to look at the limit as x approaches 2 of f of x over g of x. Okay, so this should be the limit as x approaches 2 of f over the limit as x approaches 2 of g, and that looks like 1 over, oh wait, that's a problem. Oh, and that is what I was referencing back when we were talking about rule number 5. This one right here. The limit as x approaches a of g of x cannot be 0 for this rule to hold true. Okay, so because g of x was 0, this is a no-go, and we would simply say the limit here does not exist. Okay, moving forward, don't overthink these next couple problems. Evaluating these limits really is quite simple. So as we look at this, if we use our law of limits, we are saying that it's possible to think about each of the interior limits individually. Okay, furthermore, all of these are convenient, clean. They can have the value actually plugged into them. Plugging in the value presents no problems. If plugging in the value presents no problems, you should just plug in the value. This is a polynomial function. It's smooth and continuous, so we don't have to worry about any type of difficulty for actually plugging in a value in the domain. So 5, we're going to plug it in. If we plug in the 5 for x here, we're going to get 2 times 5 squared, 2 times 25. Plug in 5 here, we get 15. Now, on the last part, there's actually no place to plug in 5, but that's okay. Evaluating the limit as x goes to 5, it's still just 4. So we're going to have 50 minus 15, which gives me 35, plus 4. Final answer is 39. Okay, now on to the next problem. This is a rational function, so there could be some values that would be problematic to plug in, but -2 is not one of them. We know that we could use our limit properties to go through and split this up into different limits we would evaluate, but because we know that, we don't actually need to do the splitting up. We can just go ahead and plug -2 straight in. Okay, and with that in play, we can go through and evaluate. We'll get -8 plus, 4 times 2 plus +8 minus 1 over, let's see, -3 times -2 is 6, so 5 plus 6 is 11. So we're going to have -1 over 11. Totally doable, very straightforward, not very interesting in my book. Finally, some spice. Now, we can bring these tools to bear on problems from the last section. They were more interesting. This is the dish you've been waiting for. What we mean to do here is to use properties of algebra to cancel problematic portions of the expression. And that is okay for the following reason. If we're looking at the limit as x approaches 1 of this equation, of this expression, we would get 0 in the denominator when we plugged in 1, but we're evaluating behavior as we approach 1. So that means it is okay to cancel things that corresponded to actually being at 1. What do I mean by that? I mean x squared minus 1 can be factored into x plus 1 and x minus 1. It would be problematic to cancel these if we were intending to physically plug one in. But if we are thinking about this simply as considering behavior as x approaches 1, then cancellation is completely reasonable. And from there, it's clear that this would be 1/2. Let's keep going in the same vein. Each of the following problems will show a particular useful technique for determining limits algebraically. On the first one, we've got the limit as h goes to 0 of 3 plus h squared minus 9 over h. So what would be nice to cancel here? What would be helpful? What is it that we can't do? What is problematic? Well, h is a 0 in the denominator sort of ruins the day. So it would be great to get rid of that, but there's not any visible h to cancel with up in my numerator. That implies that we should try expanding the numerator to start. Let's see if we get any additional options by doing that. So we're going to FOIL 3 plus h quantity squared. That'll give me 9 plus 6h plus h squared minus 9, we're still all over h. Now, I don't actually need these parentheses. These parentheses are redundant. And that exposes my 9s to cancellation. So now we've got the limit as h goes to 0 of 6h plus h squared over h. And voila, we have a common factor of h in the numerator. Limit as h goes to 0. Yes, you do need to rewrite this every time. I know some of you have already stopped doing that. You need to rewrite your limit every time. H factored out, we get 6 plus h divided by h. H's cancel. And we've now got limit as h goes to 0 of 6 plus h, which looks like 6. Classic method. Next, evaluate the limit as t approaches 0 of t squared plus 9 minus 3 over t squared. Nothing to expand in the numerator. That root really doesn't want to be helped. And no factors evident that we could cancel with down below. But I hope that part of your brain is being triggered right now by the idea of a root and an addition of some other object. We can get some nice behavior here if we use conjugate multiplication. I told you, it's a weird technique. It's non-obvious. That's why I'm doing it here to show you how. But what you want to do here is multiply by t squared plus 9 plus 3 on both top and bottom. It may go against all you see as holy because we're going to wind up with radicals on the bottom and get rid of radicals on the top doing this. But welcome to more adult math. This is where that might be helpful, so we're going to do it. Let's go ahead and think about foiling these two things out. Well, if I multiply this by that, then I wind up with root t squared plus 9 quantity squared. And if I multiply this by the negative 3, I've got minus 3 root t squared plus 9. And then by similar process, we will distribute the 3 across. That actually probably confuses things visually. So we'll just keep plowing ahead. You see the pattern now. plus 3 root t squared plus 9 minus 9. That's all the stuff that's up top. Down below, we've got t squared times root t squared plus 9 plus 3. I am not going to expand that. I don't think that's going to be helpful. We'll see if I'm mistaken, but I'm not going to do it right away. Okay, now this, come back. This term right here, the square and the square root undo one another. So we could think of this as just t squared plus 9. Next, these two terms, they cancel. Nice conjugate behavior. So we should be down to t squared plus 9 minus 9. That's rather convenient. T squared times root t squared plus 9 plus 3. Let's go a little bit further. This will just be t squared because those 9's canceled out. And what we get is the limit as t approaches 0 of 1 over root t squared plus 9 plus 3. And this is great. There's no problem whatsoever with plugging in t as 0 now. That's exactly what we want to be able to do. So we can think of this to get the evaluation as root 0 plus 9 plus 3. And last I checked, the square root of 9 is 3, so we're going to have 1 over 6.